Patty Simpson with Simpson Math. In this video, we're going to learn about the possible rational roots theorem. In a previous video, I took this polynomial and we attempted to factor it using our grouping method, and it turned out that we couldn't use our grouping method to factor it. Instead, we had to factor using synthetic division. And in that video, I had a magic hat where I just magically pulled out one of our divisors, x minus 3. And I wanted to teach you in this video how you can create your own magic hat so you can find the factors or the divisors of a polynomial. Now, before I had my magic hat, when I was trying to decide what to divide by, there were an infinite number of possibilities. I could have divided by x minus 1/2, or x plus 16, or x plus 15. There are lots of different things I could have divided by, an infinite number in fact. But in the end, there were just 3 factors for this polynomial: x minus 3, x minus 5, and x plus 2. And while creating our magic hat is not going to help us to find those exact 3, what it will do is limit the number of possibilities there are so that we know which ones are possible and which ones aren't. As we factor these polynomials, sometimes it's possible that they don't even have rational roots. Remember, we've graphed some polynomials with no rational roots at all. This theorem just lets us know which ones are possible rational roots. In other words, if it has any rational roots, what must they be? And that way we can divide synthetically by those possibilities to find the rational roots that exist. So the way that we find those possible rational roots is we divide the factors of the constant. So in this case, my constant is 30, by the factors of my leading coefficient. In this case, that leading coefficient is 1. So let me show you with this one, what would our possible rational roots be? Well, inside my magic hat, there was more than just x minus 3, because we had to do all the possible rational roots. The factors of our constant, which are 1 goes in there 30 times, 2 goes in 15, 3 goes in 10 times, 4 does not go into 30, 5 goes in 6 times, 6 goes in, it goes in 5 times, so that means now I just need the pairs, 3 times 10, 2 times 15, and 1 times 30. Each time we do this, it's going to be the positive versions and then also the negative versions, because -1 times -30 also gives me 30. -2 times -15 also gives me 30. -3, and -5, -6, -10, -15, and -30 are also all factors of 30. Then we're going to put those possibilities over the factors of our leading coefficient. In this case, the leading coefficient is just 1. So the factors of 1 are just 1 and -1. And we're going to look at all these different combinations. In other words, we're going to do this division. 1 divided by 1 is 1. 2 divided by 1 is 2. 3 divided by 1 is 3. And you can see that as I divide by 1, I'm just going to end up with all the original ones I had to begin with. So all of these are possible rational roots. And then we're going to divide by -1 for each one. Well, -1 into 1 gives me a -1. -1 into 2 gives me a -2. -1 into 3 gives me a -3. And you can see as I divide by -1, all of those possibilities are going to be here as well. So in other words, before I began with my magical hat, I had an infinite number of possibilities that I could divide by to try to find those factors. But now I know that there are 1, 2, 3, 4, 5, 6, 7, 8 doubled, so 16 possible rational roots. There are 16 possible rational roots, possibilities that were in my magic hat. I happen to pull out x minus 3. The root that was actually at 3. Because remember, as we set them equal to 0, the x-intercept there was at 3, 0. So this root represented this binomial that I divided by. There were 16 possible rational roots, but only 3 of them actually worked. 3, 5, and -2 were the 3 that actually divided into, actually gave us 0 when we plugged them in for x, gave us those root values. So we took an infinite number of possibilities and narrowed it down to 16 possibilities. And then we used synthetic division to find the actual roots, to actually factor our polynomial. Here's another polynomial. Let's make a magic hat for this polynomial. Now, in my magic hat here, I'm going to write those possible rational roots and put them in the magic hat. Let's create that. So on the first one, I'm going to do the factors of my constant. So the factors of my constant here, 15 is my constant. So those factors are 1, 2 doesn't go in there, 3, 4 doesn't go in, 5, 6 doesn't go in. Oh, I've actually already wrapped around 3 times 5, so I know it's 1 times 15. Then it's the negative versions as well. So -1, -3, -5, and -15. Those are going to be over my the factors of my leading coefficient. In this case, it's 2. So 1 is a factor of 2, and 2, 1 times 2, but also the negative versions, so -1 and -2. So these are going to be, all the combinations of these are going to be my possible rational roots. In other words, I'm going to take and divide each one. So 1 divided by 1 gives me 1. 1 divided by 2 gives me 1/2. 1 divided by a -1 gives me a -1. And 1 divided by a -2 gives me a -1/2. I'm going to do that for each of them. 3 divided by 1, 3 divided by 2. 3 divided by a -1, 3 divided by a -2. 5 divided by 1, 5 divided by 2, 5 divided by a -1, and 5 divided by a -2. 15 divided by 1, 15 divided by 2, 15 divided by a -1, and 15 divided by a -2. Now I'm going to do them with the negative versions also. -1 divided by 1. Oh, we notice that that's already there. And it turns out as I go through each one of these to do the division and look at the possibility that I've already written that one down. So for each possibility, it's there on the list. So we now know that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Again, 16 possibilities. It just worked out that both of these had 16 possible rational roots. That's not always true. Sometimes they'll have 4 rational roots, or they'll have 20 rational roots. It just depends on those different combinations. Now, as I write these down into my magical hat, I'm going to write them down as binomials, so that when I get ready to divide by, to use my synthetic division, I have a binomial I'm dividing by. Also, as I write them in linear factors, I'm writing them as binomials. So this this 1 as my root will actually be written into my magical hat as x minus 1. So the root and the binomial, remember, it changes the sign, because when I get ready to divide synthetically, I will turn that into a positive 1. And when I have this binomial and it's set equal to 0 and I solve, it ends up changing the sign on that value. So I'm going to do that for each one of them. I'm going to create my magic hat using these 16 possible roots. Now, also know that we could have one of these be a rational root as we factor it, but it's also possible that none of them work. maybe this polynomial only has irrational roots. So it is possible that none of them work. But if this polynomial has rational roots, the rational roots will be on this list. So it helps to narrow the number of rational roots that we're looking for. In other words, it helps it from going from infinity, we're down to 16 possible rational roots. So to find those possible rational roots, we take the factors of our constant, put it over the factors of our leading coefficient, and find all those possibilities. In the next video, I'm going to use my magic hat, and we're going to see if we can factor this polynomial with those possible rational roots. We'll see if any of those possible rational roots actually work, if this polynomial has any of those as roots. Math Made Simple at Simpson Math. Thanks for watching.